quite packed with stuff, to be honest. So, okay. So now we go to a completely different topic. We go to iterative methods, and iterative methods are the methods of choice for large problems. So the more we go to large problems, the more we forget about direct methods. Okay? So we'll talk about Richardson, which you already have seen, and convergence, which you already know, but except some small details which you probably do not know. And then we go to Chebyshev iteration. So if you want to achieve linear complexity with where n is the size of the matrix, if you are not solving tri-diagonal matrices, direct methods are not appropriate. Direct methods, even in the optimal case, they scale much worse than m. So for two-dimensional problems, still they beat due to efficient implementation. Otherwise, there is nothing else. And the idea is to use matrix by vector product and the subspaces that are generated by sequentially applying a matrix to a vector. This is so-called Krylov subspace. Krylov, Andrei Nikolaevich Krylov, was a great Russian and Soviet engineer. Basically developed these ideas. Again, you can read about his story. It's quite interesting. So he was like scientist guy, but then he lived very well in Soviet Union as well, academician, and made a significant contribution. Funny story is that the names Chebyshev, the name Krylov, they have been used in Western literature, but in Soviet literature, for some reason, only I think recently people start using Krylov and Chebyshev. They had different names for some reason. I don't know why. You have to promote your own scientists, but our Russian tradition is to diminish sometimes the achievements. Really the case. Krylov subspace. You just look at old books. There will be no Krylov subspaces there. So now the matrix. So for this lecture, we do not have any access to the elements of the matrix. So we only have a black box that is able to compute matrix by vector product. The subroutine that we pass an arbitrary vector and get the result of the product. What is going on inside, we are not interested. So when we want to solve linear system using matrix by vector product, and at least why it is possible, because if you can multiply matrix by vector, we can measure whether we have a solution or not. We multiply the matrix by vector, compare with the right-hand side. If the difference is small, we are done. Of course, we can cheat a little bit. If you have a matrix by vector product, we can compute the product with the columns of the identity matrix and recover the full matrix. But that's not what we want, right? The matrix is. Sometimes it's not so bad idea. If you have a black box matrix and you want to look what is inside, you just multiply it by the columns of the identity matrix and you get it. For testing, it's sometimes okay. So the Richardson iteration, again, well, I wouldn't say it's been taught in school, but well, close to that already. So, and all the iterative method, they actually start from fixed point iteration. So we write our original equation as the form x equals some mapping of x, and if this mapping is a contractive mapping, then from functional analysis we know that we will have convergence. So we have the linear system, we multiply it by a scalar parameter tau, we add the same x to the left and right side, these are equivalent transformations, and then we make this an iteration. So xk plus 1 equals xk minus tau, this guy. So what it says here is not completely wrong. When you write, it says which can always be chosen such that this method converges if the matrix A satisfies certain properties. Not always. Well, at least it should be not singular, for example. Right? Otherwise, it cannot converge to the solution. But also there are cases of non-singular matrices for which the Richardson iteration will not converge for any choice of tau. You can think about such examples, but you may guess from some of the demos we will do later on. If the main...
The property is still something about sparsity of A?
No, it's the property of eigenvalues. So if A is positive definite, for example, this will always converge. You can always find tau which is convergent. If it's not positive definite, it has to be what is called stable. So all the eigenvalues should be, which can be complex, should be located in the left half plane in the complex plane. So the real part should be less than 0. Otherwise, you may have funny things, but I will show you. So this statement is not connected at all, and this has connection to differential equation. Actually, many iterative methods, which are discrete. So what's an iterative method? You're given the current iteration, and you make a new approximation. This is, for example, what is going in stochastic gradient or in gradient descent method. You get the current approximation, take a small step in the direction of the gradient, you get to a new point, and if you make a really small step, in fact, you are solving a certain ordinary differential equation. So there is a continuous version and discrete version, and sometimes the analysis is much easier for the continuous version than for the discrete, and everything is much better presented in the continuous version, but not always the case. So you have this time-dependent problem, Cauchy problem. The derivative of y, which is our vector, plus a times y equals f with the initial condition. Then, what can be shown if the matrix A is stable? So which means that all the eigenvalues have real parts less than 0. Okay. We'll discuss matrix function, matrix exponents. If I do not forget, we'll discuss it in more details. Otherwise, just ask questions if you are interested. But if this holds, then the solution will converge to the y of t will converge to the solution. And if we write down the discretization of this derivative just by taking a simple finite difference, yk plus 1 minus yk divided by tau equal to the right hand side, you exactly get the Richardson iteration. So the Richardson iteration is the simplest explicit earlier scheme for the solution of this equation. Okay. What can we say about the convergence of the Richardson iteration? The analysis for leading case is quite easy. So if suppose our matrix is invertible and non-singular, so the solution exists, and if we just take the difference between the current iterate and the true solution, which is an error here, so f can be written as the product of a times x or y star in this case. Yeah, we have to fix notation. There was y and here is x. We have this recursive definition for the error. The error is multiplied by this matrix at each step. So what is happening? We have the same matrix and we multiply by this matrix at each step. And if you start from some initial approximation, after k step, you will have just the power of this matrix. So we need to have the property that the norm of this matrix is less than 1. Well, if you have some norm of the matrix that is less than 1, by using some multiplicativity property of the norm, we will have that the norm of ek plus 1 equals to this q to the power k, so we will have a geometric convergence to the true solution. So if we select tau in such a way, this matrix has spectral radius less than 1, okay, I said spectral radius is the tightest possible, so the norm. Spectral radius maximum absolute eigenvalue. So you have convergence, and if you have symmetric positive definite case, it is always possible, and we will show how to do it. I will show you how to do it, and you will see it many times, how to select tau that the method converges and it also converges optimally. But if A is non-symmetric, the situation is like much more interesting. If A is non-symmetric, what happens with the convergence is not so trivial. We'll see it. So if you want to minimize, if you have a symmetric positive definite matrix, then the spectral radius coincide with the spectral norm. And if you want to minimize the spectral norm of this iteration matrix, that would be an optimal parameter. it's related to the minimal and the maximal eigenvalue. So the optimal parameter is just this. This is a more or less simple exercise. To do that, what you have to do, you have to diagonalize theoretically the matrix A using unitary similarity transformation, and then it would be the problem on the spectrum, and then the second norm would be just the maximal infinity norm on the spectrum, and this is the solution. So you need to know what is the minimal eigenvalue, you need to know what is the maximal eigenvalue. You can estimate it using power method. That's one of the problems of Richardson iteration. You need to know these parameters. Okay, of course you can do it like we do in deep learning, just by random selection of coefficients, not to make only one parameter, like grid search. Okay, but for this case you can be smart. But of course, well, Richardson iteration for linear system is not what you typically use. But again, if you have just a simple iteration with a fixed point testing, for example, if you have the mapping here that is not linear but is a gradient of something. Actually, the local convergence of any iterative method in the neighborhood of the true solution is the same as using just Taylor series argument, is the same as when you approximate by a linear iterator. So and again, if you are close to the solution of our optimization problem, and we are using just the gradient descent method, that would be an optimal parameter. So in fact, we are using Richardson iteration when we go from linear problems to non-linear problems, because what's simple to use, again, we need to choose one parameter, maybe two, how we decrease this and so on. But this linear approximation, of course, it's true only around near the origin, and there are other regions, but still. So for linear, we often use sort of Richardson iteration because, well, it's quite robust, at least it converges. Yeah, for non-linear problems. For linear problems, it's not a practical way, but from theoretical viewpoint, it's interesting to look at the convergence of the Richardson iteration. So if you put this, and this is very instructive formula, this is how this norm of this iteration matrix behaves. So the norm of this iteration matrix is exactly the condition number of the matrix A minus 1 divided by condition number of matrix A plus 1. This is strictly less than 1, but if condition number is large, even it's 100, this number will be very close to 1, and the convergence will be extremely slow. So this is another manifestation of the condition number. So remember, the original property of the condition number was the perturbation bound. So if you know the matrix approximately, if you know the right-hand side approximately, the solution that we get is up to condition number times the error, right? So condition number of the matrix is the measure of the forward stability of solution of linear systems. But it also enters here, if you try to solve a linear system, if the system is bad for a Q in terms of forward stability, it's also bad in terms of iterative methods. So it simultaneously measures both the forward accuracy and also how complex this matrix is in terms of solving linear system with it. If the matrix is ill-conditioned, okay, the problem with accuracy if you use double precision is not so vivid, because typically if you have condition number 10 to the power 4, 10 to the power 5, the accuracy that you will get would be machine precision times to the 10 to the power 4, would be 12 digits, and typically for large-scale problems you never need 12 digits, you may need 3 or 4 digits of accuracy. There is no problem with accuracy, but if you run this method, you will just, if condition is 10 to the power 4, you will just wait infinite amount of time for the convergence. It will be very slow. And for symmetric positive definite case, of course, you have monotonic convergence. So here the condition number is 45, and that's how the error decays. So after 100 of iterations, we go to 10 to minus 1. So decrease monotonically, but very slow. And here we measure the norm of the error. So that's what we expect. We slowly, but consistently, in a monotonic way, go to the convergence. So that's the summary of what you said. So if you have ill condition matrix with large condition number, you will need a lot of iterations to solve a linear system, which makes the whole method useless. Even if you have matrix directed product fast, if you need millions of iterations, it would be faster just to use, for example, fast direct method. And that's the key idea here. What people are doing is to use so-called preconditioners. So precondition, you have a linear system AX equals F. You can multiply, for example, this system of equations from the left by a certain matrix P, which is called preconditioner. P times AX equals P times F, in the hope that P times A will be better condition. So in order to solve the problem with conditioning, we use preconditioners. So the ideal preconditioner will be the inverse of the matrix. You cannot compute the inverse, but who said you need inverse with very high accuracy? Even a very crude approximation to something looking like an inverse may give you an excellent precondition. And then, and without it, nothing works, and there is a whole bunch of family of preconditioners for different problems. So we will discuss it, and it is not possible to solve